But this is part 6 of the course described as analysis of closed systems. And what we're looking at here is we're looking at moving boundary work for quasi-equilibrium processes. And we're going to do a general energy balance then for closed systems. So just a brief recap. Work is defined as the energy transfer associated with a force acting through a distance. So when you push that box across a room, then it's the force required to push that box multiplied by the distance that it's displaced will give you the work done during that process. And the forces in newtons, the distances in meters. So 1 Newton meter equals 1 joule, which is the SI unit for work. In part 3, we introduced different types of work. One we touched on was piston work, and that's where we're going to put a focus on now. So to explain what we mean by moving boundary work, here we have a piston-cylinder device, and it's a closed system, and the boundary is defined by this dotted line. But when we heat up the gas and the gas expands and the piston moves, we can see that the boundary moves with it. So that's why we call it moving boundary work. Quasi-equilibrium process, also known as quasi-static process, refers to a thermodynamic process that occurs so slowly that the system involved can be considered to be in a state of equilibrium at every stage. So these piston devices move very, very quickly, back and forward very quickly, to the extent that the idle speed of an engine would be about 1,000 RPM. So they can go much higher than that. So because of that, we're not certain that when a piston moves from one state to another, at any particular position that piston is in, we can't necessarily say for certain that the pressure and temperature and other thermodynamic properties would be of a particular value, because the system is constantly trying to restabilize itself. The reality is there's probably a range of pressures and a range of temperatures in here, but that's very difficult to analyze. So what we assume is that it is in equilibrium, and the quasi here means as if in equilibrium. And the theory, the process paths, and the work that we define in these processes and the values approximate very closely to what they would measure in experimental tests and produce with simulation software. So the moving boundary work, to calculate moving boundary work, the differential amount of work done when we heat a gas up and increase the pressure, and there's a force applied to the piston and it moves by a differential amount ds, is the force multiplied by that differential amount ds. Now we know there's a relationship between pressure, force, and area. So the pressure in the gas equals the force acting on the piston divided by the area of this piston here. So we can rearrange that to get force equals pressure by area. So we can replace force over here by pressure by area. There's another important relationship in there, and it's the area by the distance displaced will give us the differential volume that's displaced. And so our boundary work equation, we want to find the total work done between two states. We integrate between states 1 and 2. Integrate P dV between those two states. If we were dealing with an isobaric process, that's a process that occurs at constant pressure. We can take the P out of the integral and we integrate between states 1 and dV between states 1 and 2. And we simply get pressure by V2 minus V1. Now, if we were to plot that on a PV diagram, it would look like this, a straight line plot between V1 and V2. And if we were to get the area under that curve, it would be the pressure by that change in volume. So we can see that the area under this process path equals the boundary work done. So what we can say is that if we get the area under a process path here, we get the work done during that process. Unfortunately, not all processes follow straight lines, and most of them will follow curved lines like this. So what we need to do is we need to get the equation of that line and integrate it between the two states to get the work done during this process. There's a number of standard thermodynamic processes that occur often enough and have something uniquely identifiable about them that they're useful to look at and analyze to try and understand the theory. And that's what we're going to go through now. We're going to go through those standard processes and explain how we calculate the work in these processes. So first one is an isochoric process that occurs at constant volume. And we have an isobaric process, which you've just seen, that occurs at constant pressure. An isothermal process, constant temperature process where PV equals constant. In other words, P and V change at the same rate. Adiabatic process where there's no heat transfer between a system and its surroundings. And a polytropic process associated with the compression or expansion of a gas, which includes heat transfer and follows the law of PV to the power of N equals constant. So let's look at each of those in turn. So this one is the isochoric process. The analogy there would be a pot that's being heated up, but the vapor doesn't get an opportunity to expand and increase the volume. In the piston-cylinder device, it's the piston being held rigidly in the one position. And if we plot it on a PV diagram, it looks like this, a line of constant volume. And obviously, there's no area under this curve. There's no work being done by the process. The integral equals 0. So there's no boundary work being done in this process for that reason, because there's nothing moving and therefore there's no area under the curve. Simple example, a rigid tank contains air at 500 kilopascals and 150 degrees C. As a result of heat transfer to the surroundings, the temperature and pressure inside the tank drops to 65 degrees and 400 kilopascals respectively. Determine the boundary work done during this process. As the air in the rigid tank is cooled, both pressure and temperature drop. Since there's no volume change, there's no work done during this process. So we go from this state down to this state. It's a rigid container. Once again, nothing's moving. There's no area under the curve. The integral equals 0. This one is called an isobaric process, and it occurs at constant pressure. And the analogy there would be if we took the lid off the pot and it's exposed to atmospheric pressure, so the pressure would be constant all the way through. And basically in the piston cylinder device, it's the same force acting on the piston. And it's a straight line plot at constant pressure between the two states. And as we've seen previously, it's simply pressure by change in volume. And simple example here, a piston cylinder device initially contains air at 150 kilopascals and 27 degrees Celsius. At this state, the piston is resting on a pair of stops. And the enclosed volume is 400 liters. The mass of the piston is such that a 350 kilopascal pressure is required to move it. The final temperature is 1127 degrees. So find, first of all, the final volume and the work done. So the first process starts here. And as the pressure increases, there's no change in volume because the piston stays on the stops here. It's not until we reach this pressure does the piston start to move off those stops. And as it does, the pressure stays constant and the volume increases. So we know there's no area under the first curve. There's nothing moving at this stage. So this is an isochoric process, a process at constant volume. So all of the work is being done by this second process here. We know the pressure, we know the initial volume, but we don't know the second volume. So to get the second volume, we can use the combined gas law over here. We have the initial pressure, we have the volume, we have the temperature in Kelvin, we have the second pressure or the pressure. So we're operating between 0.1 here and 0.3. And so at 0.3, we have the pressure as well. We have the temperature. So what we need is the volume at 0.3. And it works out at 0.8 meters cubed. So now we have enough information. We have V3, we have V1, and we have P3. And we put that into our equation, and we get 140 kilojoules is the amount of work done to lift that piston off its stops. Isothermal process. So this is a process that occurs at constant temperature. So basically what we're doing is as we heat it up, we regulate the temperature and make sure it doesn't go over a certain value. So that's the analogy there. And the same thing in the piston cylinder device over here. And this follows the rule PV equals C. So what we mean there is P V multiplied by V at this point equals P multiplied by V at this point equals P multiplied by V at this point, and so on. In other words, P by V equals constant. We can rearrange that expression to get P on its own. P equals C over V. And in our boundary work equation, we replace P with C over V. We take C out of the integral because it's a constant. And we integrate 1 over V dV between states 1 and 2. And we get C ln V2 over V1. And then we replace C in terms of V1 and P1. And that's our boundary work equation there. So in this case, this example here, a piston cylinder device contains 0.4 meters cubed of air at 100 kilopascals and 80 degrees. The air is now compressed to 0.1 meters cubed in such a way that the temperature inside the cylinder remains constant. Determine the work done during this process. This is our boundary work equation. We have P1, we have V1, we have V2 and V1. And in the equation, it turns out to be minus 55.5 kilojoules. So it's a compression. So what's happening there is we're taking there's work being produced by the environment, work done on the system by the environment. So we have a negative value in here during the compression. If it was positive, it would mean the system's actually doing work for us and giving it to the environment. An adiabatic process is a process in which there's no heat transfer between a system and its surroundings. An adiabatic boundary does not permit heat transfer. And the analogy there would be just a very well insulated system. So insulating the pistons extremely well so that there's no heat transfer. And it can be shown that the boundary work is P2 V2 minus P1 V1. That's all over the adiabatic index minus 1. So the adiabatic index is the ratio of the specific heats that we would have covered in the previous section. So the next one then is a polytropic process. The derivation for the polytropic is the same as the derivation for the adiabatic. So we'll derive the polytropic process now. It's associated with the compression or expansion of a gas, which includes heat transfer and follows the law PV to the power of N equals constant. So say that P multiplied by V to the power of N here equals P multiplied by V to the power of N here, and so on. So what we can do is we can rearrange that expression, and we get P equals C over V to the power of N. And our boundary work equation is P by dv. So what we do is we replace P in terms of C over V to the power of N. Take C out of the integral. Now bring that onto the next page. We have dV over V to the power of N. And that's the same as V to the power of minus N. And if we integrate that, it's V to the power of minus N plus 1 over minus N plus 1. But now we integrate it between states 1 and 2. And this is what we get. We multiply C back in terms of P and V. So we've got P2 V2 over here and P1 V1 over here. Now we add the integrals here when we're multiplying them together. So V to the power of N multiplied by V to the power of minus N plus 1. The n's cancel and you're left with V2 to the power of 1, which is just V2, and that's what we get down here. And the same on this side of the equation. V to the power of N multiplied by V to the power of minus N plus 1. The n's cancel and you're left with V1 to the power of 1, which is just V1. So this is how we arrive at this expression down here, and we're just literally just moving these around to tidy up the equation. The polytropic process that we've just done is a versatile and can be described a wide range of thermodynamic processes by varying the values of n. So n is a real number that's typically within the range of 1 to 1.7. So for example, down here in this equation, if we let n equal 1, n equals 0, then v to the power of 0 is 1. So that just means that p equals constant. And that's equivalent to an isobaric process at constant pressure, and that would be this line up here. If we let n equal 1, v to the power of 1 is just v, so pv equals constant, equivalent to an isothermal process, a process at constant temperature, so that would be this line here. If we let n tend to infinity, v becomes so much bigger than p becomes negligible, so it's essentially v equals constant, equivalent to an isochoric process, allowing a constant volume here. And then when n equals the adiabatic index, it's equivalent to an adiabatic process in which there's no heat transfer, and that's this process here. So all of those previous processes are basically versions of the polytropic process with special cases for the n value. So this is a summary of the different values, the different boundary work equations. Here's an example of a thermodynamic cycle that brings all of what we've done so far together. So this consists of 4 processes: the polytropic process, an isochoric process, another polytropic process, and then another isochoric process. And what we'll do, it's basically a piston compressing itself, the pressure going up, then an expansion or like a power stroke, and then an exhaust. So this will be kind of similar to maybe the Otto cycle that describes how a petrol engine works. So you have compression, and then you have ignition as the pressure increases at constant volume, and then you have the power stroke that's delivering work to the crankshaft, and then what you have is you have an exhaust here to bring it back down to the original pressure. Now, during this, to get the work, the network that's being produced by the system, we need to get we need to calculate the work done during each of these 4 processes and add or subtract them accordingly to get the network done in the middle here. And that's ultimately the work that's been that would be used to, let's say, drive the car. So when this power stroke occurs, there's a lot of work here being delivered to, if it was a petrol engine, to the crankshaft. But then as the crankshaft rotates, it compresses, so it gives some work back into the system. So we basically have to take these values away from each other to get the portion in the middle to find out ultimately how much work is being provided by this system. So let's read this example. Air at a pressure of 0.1 megapascals is enclosed by a cylinder and a piston. So that's down here. Its volume is reduced to 1 liter, from 1 liter to 1/8 of a liter. That's here. In a polytropic process with an exponent n of 1.4. The pressure is then increased at constant volume to 4.8. So at this position, the pressure is dramatically increased. The air is brought back to its original volume in another polytropic process with the same exponent. It is then brought to the initial pressure in a constant volume process. So this is the power stroke here, and then there's an exhaust. So what we want to do is sketch that and then calculate the work done for each process and calculate the average power output if there's 3,000 cycles per minute. So what we're going to do is we're going to plot this. And to plot it, we have the pressure and the volume at this point. We're going to assume different points, different volumes to represent positions along this curve. And then with the polytropic relationship, we will find out what the pressure is at those values. And so that'll give us enough information to plot this curve. And we will do the same with this curve, and then we will join up these 4 points and then ultimately get the work done by adding or subtracting accordingly. So that's what we're going to do. We're going to use this relationship here to plot this curve. We're going to work out the C value. We're going to assume the V values. We're given the N value, and then we'll work out the P values, and we'll have enough points to plot this line and do the same between states 3 and 4 as well. So this is our polytropic. This is the polytropic equation here. PV to the power of N equals constant. So what we need to do first of all for state 1 down here is calculate the constant. So we have the pressure at that point. The volume, we have it in liters, but we just need to convert it into meters cubed. We have the polytropic exponent, and we work out the C value. So now what we do is we transpose this equation over here, get P on its own. We assume different values for V. So we assume half a liter, and then it's a quarter of a liter, and then 1/8 of a liter as well. So at half a liter in meters cubed, with the constant here and the polytropic exponent, we work the pressure out to be 0.264. So the pressure here is going to be 0.264 with 10 to the power of 6 newtons per meter squared. At a quarter of a volume, it works out to be 0.696. And then at 1/8 of a volume, it works out to be 1.838. So we have our pressures and our volumes, and we can plot this line roughly. And we do the same with the second polytropic process between states 3 and 4. We have our polytropic equation. So we have the pressure at this point. We know that, and we know the volume. And we have the polytropic index. And this time we work out the exponent, which is, the constant, which is different for this line. And we'll assume that the volume is a quarter, a half, and full volume in this case. So in the first case, we have our constant, we have the volume that we assume, and then the polytropic index, and we work out the pressure at that volume to be 1.817 by 10 to the power 6 newtons per meter squared. For half a volume, it works out to 0.686, and for a full volume, it works out to be 0.281. So we have enough information now to calculate the work for each of those processes. So between states 1 and 2, that's between here and here, we have P1 and V1, we have P2 and V2, we have the index. So we put those values in, and the work is turning out to be minus 324.4 joules. It's compression, so it's work being provided by the environment to compress that gas. For the second process between states 2 and 3, it's isochoric, so there's no work. And that's the same for process 4 to 1 during the exhaust. There's no work being done either there. So for process 3 to 4, we have the pressure and volume at states 4 and states 3. We have the polytropic index as well. And the work turns out to be 847.5 joules. So there's work being done on the environment, so it's positive. But when we work them out, we see there's a net value of 523.1 joules. So there's a net positive amount of work being done on the crankshaft or whatever system it happens to be. If we multiply that by the revs per minute, which is 3,000, and divide that by 60 to get it into seconds, we have the rate of doing work, which is power. So that works out at 26155 watts or 226.155 kilowatts. So if this was an engine, for example, that would be theoretically telling us how much power can be provided by this cycle. And we can confirm that with experimental data, for example, or from software simulations and things like that. And we can compare that by varying the processes in some way to see which ones are more efficient than others and so on. Right, so just going through some common thermodynamic cycles to show you where those processes occur. So the thermodynamic cycles are processes that convert heat energy into work and vice versa, typically used in engines, refrigerators, and power plants. These cycles involve a series of thermodynamic processes that return a system to its initial state. And here's some common thermodynamic cycles. The Otto cycle. An Otto cycle is a thermodynamic cycle that describes the idealized process of a four-stroke internal combustion engine, typically found in petrol engines. It involves four main processes, two adiabatic and two isochoric. So you've got the two adiabatic here, no heat transfer, and the two isochoric. The real Otto cycle, there would be heat transfer, and then you've also got an intake and an exhaust. So these cycles are idealized, and there's no heat, generally no heat loss, no friction and losses like that involved. But they do approximate to what happens in the real world, and they're good for analyzing and comparing to other versions of the cycle to see which ones will be more efficient. You've got the Rankine cycle. It's a thermodynamic cycle used to convert heat energy into mechanical work, typically employed in power plants, and involves phase change of water into steam. It involves two adiabatic and two isobaric processes. So these ones here are the isobaric at constant pressure, and then these ones would be the the adiabatic with no heat transfer. These ones here, and these are the isobaric. And then we've got the vapor compression cycle. It's widely used in refrigeration systems, such as household refrigerators, air conditioners, and commercial refrigeration units. It involves the use of a refrigerant that cycles through different phases to absorb and release heat, thus providing a cooling effect. The cycle involves two adiabatic and two isobaric. So these are the isobaric, and these are the adiabatic. And the Brayton cycle, also known as the gas turbine cycle, is a thermodynamic cycle that describes the workings of heat engine, commonly used in jet engines, gas turbines. And the cycle involves two adiabatic and two isobaric. So these are the isobaric once again. And these are the ones adiabatic here with no heat transfer, and isobaric constant pressure. And the diesel cycle, it's a thermodynamic cycle that describes the idealized operation of a compression ignition engine, commonly known as a diesel engine. It involves two adiabatic, an isobaric and an isochoric process. So you've got the isobaric here, you've got the two adiabatic ones here, and then you have the isochoric process.